Hi everyone, we're going to take a look at absolute value graphs on the coordinate plane. We're going to start by looking at what we call the parent function. That's basically where we have a relation between x and y and we don't add or subtract or change any of the coefficients of this. It's just a plain old y equals the absolute value of x. So the parent function of this graph looks like this. It has its vertex point at the point 0, 0. And you'll notice that it has a nice steady even slope of just 1. That means 1 over 1 as we go along to the right. And from the vertex point through the left side of the graph, this is an actual reflection of every single point on the right. In other words, if I were to look at the point 1, 1 on the right side of this graph, and then look for its reflection to the other side, it would be at negative 1, 1. If I were to look at the point 5, 5, its reflection is going to be at negative 5, 5. And the reason that that's true is we're dealing with absolute value, and absolute values are always going to be positive. Notice that we have no numbers that are below 0 for the value of y. Y is equal to the absolute value. X can be any number, but y is going to be the absolute value, and there's no such thing as a negative absolute value as long as it's not been shifted, as long as the function has not been shifted. So for the parent function, we're looking at all positive values. Every time I plug in an x, its absolute value will be a positive number. Now, you may notice that the line that goes through this vertex point looks like it might be the line where everything reflects. And that's true. All of the points reflect across that line. Notice that from 1, 1, I go across to negative 1, 1. From 5, 5, I go across to negative 5, 5. That point, these sets of points are equidistant to this y-axis. The reason that that's true is that this axis, or this line, this vertical line that goes through the vertex point, is called the axis of symmetry for this graph. We'll talk about that a little bit more, but the axis of symmetry is always a vertical line that goes through the vertex point. Now let's see what happens when we add 4 to our parent function. You'll see that our original function has its vertex point at 0, 0, but when we add 4, the vertex point has shifted up 4 units. That's because we have taken the absolute value function and moved it up vertically. This plus 4 moves all the y values up 4 units. The axis of symmetry is still in the same place. The line of reflection is still in the same place. The only thing that's happened is all of the points from the original graph have moved up 4 units. So if when we add 4 to our parent function, the graph moves up 4 units, then what do you suppose happens when we subtract 1 from the parent function? Probably guessed that it will move down 1 unit. So notice that our original function had its vertex at 0, 0. The new function has its vertex at 0, negative 1. Now we do have some negative y values, and that's because what we've taken is we've taken our y values, our original y values, and we've subtracted 1 from every single one of them. So it's pulled the graph down 1 unit. The axis of symmetry is still in the same place, so all the reflective points still reflect across that same line. The only thing that's happened is it's shifted down. So we know what happens when we add to the parent function and when we subtract from the parent function. But what if we actually change the function so that we're adding inside the absolute values? That means that we are subtracting or adding to and from the x inside the absolute value before we take its absolute value. So let's take a look at this graph and compare it. Now the original absolute value had its vertex point, or the original parent function had its vertex point at 0, 0. And our new function, where we have subtracted 2 from the value of x, is now at a vertex of 2, 0. It's actually pushed the graph 2 units to the right. And you might be wondering why that has happened. Well, let's say that we had put in 0 for the value of x. When you put in 0 into the original function, you'll get 0, 0. But when you put 0 into our new function, right, the absolute value that you'll find will be the absolute value of -2, and the absolute value of -2 is actually going to be 2. Notice that when x is -2, the y value, pardon me, when x is 0, the y value is 2. Now, that's a lot to remember and a lot to think of. One thing that you can say for sure is when you subtract from the value of x, it kind of pushes it forward that many units. So if subtracting from the value of x pushes it forward, then what would adding do to the graph? Well, you probably guessed that it will pull it back that many units. So by adding 3 to the value of x inside the absolute value, we actually pulled the graph back 3 units. Otherwise, these graphs all have a very similar look. The slopes of both sides of each of these absolute value graphs are exactly the same. The axis of symmetry has changed. So if I focus just on the one where we subtracted 2 from the value of x, notice that our axis of symmetry has shifted over 2 units as well. The line where it's reflecting is now where x equals 2. It's going through this vertex point. And if I focus on the graph where we have added 3 to the value of x and where it's been pulled back 3 units, the axis of symmetry has also been pulled back 3 units. So it's where x equals -3. Remember that the axis of symmetry always goes through the vertex point. So now we're going to take a look at kind of combining some of these shifts, these translations, all in one. We know that when we add to the absolute value function, it will move it up. When we subtract, it will move it down. When we subtract from the x inside the absolute value, it will shift it forward. When we add to the x value inside the absolute value, it will pull it back. So let's look at this particular function right here. When we subtract 3 from the function, that should pull it down 3 units. And when we add 1 to the value of x, that should pull it back 1 unit. So let's see if that's what happens. Remember, our original vertex point was at 0, 0. We said this should push it down 3 and pull it back 1. So if I count down 3, 1, 2, 3, and back to the left 1, I do find my vertex point is, in fact, at -1, 3. So it is where I expected it to be. Otherwise, the slopes look the same. The axis of symmetry has pulled back by 1, so it's the vertical line where x equals -1. So let's compare that with the next graph. This is going to be a little bit different. We know it's going to push up 1 unit, and you might suspect that it's going to be pulled back 5, but we have this other coefficient in front of the x that's going to affect that horizontal movement just a little bit. Let's take a look at that by itself. Notice that our vertex point did shift up 1 unit, but it did not pull back a full 5 units. So what happens when you have an absolute value function where you've got a coefficient other than 1 inside the absolute value is that it affects the horizontal movement, meaning it sort of changes it. So the way we find it is we take the entire expression inside the absolute value, this 2x plus 5, we set it equal to 0, and then solve for the x. So if I take this 2x plus 5 and solve it for x, when I've set it equal to 0, I would get a -5/2. And that is, in fact, -2.5. Notice that that is actually the x value for this vertex point. And that is also where the axis of symmetry will be. So let me say that again. Although this got pushed up 1 as expected, because we have a coefficient that is not 1, what we have to do is say, you know what, this is going to be set equal to 0 and then solved for x. So if I set 2x plus 5 equal to 0, I'll get negative 5 halves, and negative 5 halves is actually negative 2.5. So that's how we technically find our vertex point for our graph. Now notice that the slope looks a little different. It's a little steeper than this original parent function. In fact, it has taken, the right side of this graph has taken on the slope of this coefficient inside the absolute value. If you were to look at this as like an mx plus b, this would be the slope of the right side of this absolute value function, and then it's just reflected across our axis of symmetry accordingly.